In the last video, we introduced indeterminate forms and L'Hopital's rule. We said if we are computing a limit, and that's a limit of a quotient of two functions, and the numerator and denominator both approach zero, or the numerator and denominator approach plus or minus infinity, in those cases, L'Hopital's rule is appropriate. So in that case, we say, okay, if we have a 0 over 0 indeterminate form and the numerator approaches 0 faster than the denominator, we should get 0. And because 0 divided by a number is 0. If I have a finite number, a non-zero finite number divided by 0, meaning that the function in the denominator approaches 0 faster, I would expect plus or minus infinity. And if these both approach 0 at the same rate, we might expect to get a finite number. That suggests that the limit as x approaches c of f of x divided by g of x is the same as the limit as x approaches c of f prime of x over g prime of x. Because we're saying, well, how do we measure this sense of this function approaching 0 faster than this one? Well, we use rates of change, the instantaneous rate of change of f, and we divide by the instantaneous rate of change of g. And basically we do this, and then if this function is continuous at x equals c, we just plug in x equals c and then we're done. If this function is still an indeterminate form, then we can use L'Hopital's rule again. But again, L'Hopital's rule only applies if we have this infinity over infinity, plus or minus infinity over infinity indeterminate form, or a plus or minus, well, it's just not plus or minus, 0 over 0 indeterminate form. If we have one of these other types of indeterminate forms, we've got to do something else. And this one is primarily what this video is about. We're only going to do a couple of examples like this. I've included a couple of other examples as well that aren't indeterminate forms, just to make sure that we're actually deciding whether or not L'Hopital's rule is appropriate before we apply it. But we will talk about how to handle this and using L'Hopital's rule, or how to handle this algebraically so that we can use L'Hopital's rule in this video. But there was one problem that I wanted to talk about again from the last video. It was this problem, example 4, where we had the limit as x goes to infinity of x cubed divided by the natural log of x to the 4th. We said that this function is going to infinity and this function is going to infinity, so we have an infinity over infinity indeterminate form. When we evaluated the limit, the final limit turned out to be infinity. I just wanted to show you that numerically on Desmos.com. So let's look at that. This is the last example that we did at the end of the previous video. Our f of x is at x cubed. And the g of x is that natural log of x to the 4th, which is just like 4 times the natural log of the absolute value of x. And we said, which one goes to infinity faster? I think the x cubed obviously grows faster than the natural log function does. So we're interested in that quotient of f of x divided by g of x, which I'm calling h of x, as x goes to infinity. So to evaluate that limit or explore that limit numerically, we can just substitute in larger and larger x values to our h function. And we see that when x equals 10, we get 109 approximately. When x equals 100, we get 54,286. When x equals 100,000, we've got 2.17 times 10 to the 13th. So the h is getting larger and larger very, very fast as x goes to infinity. This is much, much larger than the x value that it corresponds to. And we can see that when we look at the graph of h. So it's pretty clear from this table that the limit should be infinity. But if we want to find that limit algebraically, we can take the derivative of the numerator and derivative of the denominator and explore that limit instead. The limit of, or the derivative of x cubed is 3x squared, and the derivative of that 4 times the natural log of x is 4 divided by x, or it's the same derivative that you get if you take the derivative of natural log of x to the 4th. So if we look at a table of values for this, f prime divided by g prime, we see that as x gets larger and larger, f prime divided by g prime also gets larger and larger. So we could graph that if we wanted to. We'll just say, I don't want to call it h, let's call it y equals f prime divided by g prime. And we see that that function actually gets very, very large. And actually, when we divide these, we end up with 3/4 of x cubed. So we just end up with this cubic function. And of course, as x goes to infinity, the cubic function goes to infinity. So that's one way that we could explore those limits at infinity numerically, just by making a table of values on Desmos.com. So this video is about 0 times plus or minus infinity indeterminate forms. And here's an example. It looks like a product, so I might think that I've got that type of indeterminate form. So what happens to the function square root of x times natural log of x as x goes to infinity? Well, natural log of x looks like this. As x goes to infinity, natural log of x goes to infinity. And square root of x looks like that. As x goes to infinity, the square root of x goes to infinity. So I've got a very large number times a very large number. So the product is very large. This is not an indeterminate form. It's just infinity times infinity. So of course, a large number times a large number is a large number. And this will get larger and larger as x gets larger and larger. So the limiting, it's not a limiting value, but the limit doesn't exist. It doesn't exist in a very specific way. The function approaches infinity. Now this one is a product as well. As x goes to infinity, x cubed minus 4x, that's a cubic polynomial that goes to infinity. And e to the negative 2x, well, that goes to 0. Because remember, e to the negative 2x looks like this. When x is a very large number, we have e to a large negative power. Let's say we had e to the negative 1,000. Using our exponent properties, we know that that's 1 over e to the 1,000. E to the 1,000 is a huge number. 1 divided by a large number is a very small number. So this function is approaching 0. And these are very, very tiny positive numbers as x goes to positive infinity. The cubic function, I'm not actually sure where this particular cubic function or what this particular cubic function looks like. I know that when x equals 0, we get 0. And when x equals, I think, 2, we also get 0. So I imagine it looks something like this. I don't know. I'm not 100% sure. Something like that. But as x goes to infinity, the cubic function goes to infinity. So I've got something that's approaching infinity and something that's approaching 0. So this is a 0 or an infinity times 0 indeterminate form. Now, in order to use L'Hopital's rule, we have to rewrite the expression as a 0 over 0 indeterminate form or an infinity over infinity indeterminate form. And the way we typically do that is we want to write this as a quotient, right? So we can either take the reciprocal of this and put it in the denominator, or take the reciprocal of this and put it in the denominator. Because when you're multiplying by some function, it's the same as dividing by the reciprocal, or dividing by a number is the same as multiplying by the reciprocal. So it still works either way. So what I tend to do, or what I tend to think of, is I've got that negative exponent. So I'll think of it in terms of this exponent property. E to the negative 2x is actually 1 divided by e to the 2x. 1 divided by e to the 2x times this polynomial divided by 1. If I multiply straight across, gives me that e to the 2x in the denominator. Now I have an infinity over infinity indeterminate form, and L'Hopital's rule is appropriate. So when I take the derivative of the numerator, and I take the derivative of the denominator, the limit of this expression is the same as the limit of that expression by L'Hopital's rule. So then you say to yourself, okay, now can I evaluate this limit as x goes to infinity? Well, as x goes to infinity, I've got the numerator approaching infinity, and the denominator is still approaching infinity. So we still have an infinity over infinity indeterminate form. So we'll use L'Hopital's rule again. Take the derivative of the numerator, we get 6x. Take the derivative of the denominator, we'll have 2 times the derivative of e to the 2x, which is e to the 2x times an extra 2. The 2 times 2 is going to give us a 4 out front. And we still have an infinity over infinity indeterminate form. So we will use L'Hopital's rule a third time. We get 6 divided by 4 times the derivative of e to the 2x. Derivative of e to the 2x is e to the 2x times the derivative of the inside, which is 2. And now you might be tempted to just take the derivative again, but of course you don't want to do that. You want to check what happens to this function as x goes to infinity. Well, it's 6 divided by a really large number, so it's going to be a really small number. So we get 0. So this infinity times 0 indeterminate form turned out to give us a 0 value. So that means this function approaches y equals 0 as x goes to infinity. So y equals 0 is a horizontal asymptote of this function. All right. Now this one is already a quotient. So this type of indeterminate form is not even possible. But you might think, okay, is this limit an indeterminate form? If I plug in x equals pi over 2 here, do I have a 0 over a 0 or a plus or minus infinity over infinity? And it turns out I do, because the cosine of pi over 2 is 0, and pi over 2 minus pi over 2 is 0, so I've got 0 cubed in the denominator. So that is a 0 over 0 indeterminate form. So if I want to evaluate that, I can just use L'Hopital's rule directly. I don't have to do any rewriting first because I don't have that product. If I had a product, I would need to do some rewriting like this to write it as a quotient, and then we could apply L'Hopital's rule. But this time, L'Hopital's rule applies directly. So we'll just say, by L'Hopital's rule, that limit is equal to this limit. The limit as x approaches pi over 2 of the derivative of the numerator divided by the derivative of the denominator. The derivative of the denominator requires the chain rule. The derivative of a function cubed is 3 times that function squared. Put the inside function back inside and multiply by the derivative of the inside. The derivative of a constant minus, or x minus constant, is just the coefficient of x, which is 1 in this case. So we say to ourselves, okay, is this function continuous at pi over 2? Well, if I substitute in pi over 2 here, remember what sine looks like. At pi over 2, we actually get a 1 for sine. That's what y equals sine of x looks like. So the numerator is actually approaching -1, and the denominator is approaching, well, 0. So I'm going to have -1 divided by 0. So that's either going to be positive or negative infinity. And as I approach pi over 2 from the left or right, that x minus pi over 2 squared is always going to be positive. So we're going to have -1 divided by a tiny positive number. It's going to be -1 times a large positive number. So we're going to end up with negative infinity. So what does that mean? That means that x equals pi over 2 is a vertical asymptote of the function. Because the limit as x approaches that value is negative infinity. So I don't know what the entire graph looks like, but I know that as we approach pi over 2, from the left or the right, the y values on the graph go to negative infinity. So that's what that limit tells me. Okay, last one. We've got the limit as x approaches 0 from the right of 0, or excuse me, x cubed times cotangent of x. Now cotangent, remember, is cosine of x divided by sine of x. So initially, if you don't remember your trig identities or reciprocal identities, you might not recognize this as an indeterminate form, but it is an indeterminate form. There's a quotient here. As x approaches 0 from the right, the cotangent approaches positive infinity. If you don't remember what that graph looks like, you can always just write that, rewrite this expression as x cubed times cosine of x divided by sine of x. As x approaches 0 from the right, cosine of x is approaching 1, and sine of x is approaching 0, but it's a tiny positive number. So I have 1 divided by a tiny positive number. That means this function, cotangent of x, is approaching positive infinity as x approaches 0 from the right. In trouble getting my cap off there. And as x approaches 0 from the right, of course, 0 cubed is 0. So we've got a 0 times infinity indeterminate form. Again, we cannot apply L'Hopital's rule until we write it as a quotient, but with our trig functions that are defined in terms of quotients, that's relatively easy. We just say cotangent of x is cosine divided by sine. multiply straight across with that x cubed divided by 1, and you get this new quotient. If I plug in 0 to the numerator, I get 0 times 1, which is 0. If I substitute x equals 0 into the denominator, I also get 0. So now this 0 times infinity indeterminate form, and I like to put it in quotes because it's not equal to infinity, it's just approaching infinity, becomes a 0 over 0 indeterminate form. Then by L'Hopital's rule, we take the derivative of the numerator and divide by the derivative of the denominator. The derivative of the denominator is easy. Derivative of sine is cosine. And the derivative of the numerator requires a product rule. We have the derivative of the first function, where that's my first function, so 3x squared times the second, plus the derivative of the second function, derivative of cosine is negative sine of x. And then we multiply by the first function. And the question is, what happens as x approaches 0? Well, the numerator is still 0 because I've got these factors of x squared and x cubed here. And then the denominator is approaching 1. So I end up with 0 divided by 1, which is 0. So it was not indeterminate, even though it looked a little bit scary at first. And when we substitute x equals 0, the function in the denominator approaches a non-zero number. So we get a limit that is finite. So as x approaches 0 from the right, this function approaches 0. So this function has a removable discontinuity. Or, well, actually, I don't know if it's for sure that it's removable. Probably removable. As x approaches 0 from the right, we know that the y value on the graph is approaching the origin, or the curve itself is approaching the origin as we approach from the right. I don't know if it's approaching from above the x-axis or below the x-axis, but it's going to look something like that. Now, I'm not really sure what happens from the left, but I don't think anything would actually change from the left, would it? If we were approaching from the left, this would be a 0 times negative infinity indeterminate form. But all of our calculations would have been exactly the same, and we would still have a 0 divided by 1. So I think that should be fine. I think the limit from the left and the right should be the same. Although the form of the indeterminate form wouldn't be the same, because when you look at this cotangent function, it actually has different limits on the left and right of 0. So cotangent actually looks like this. It has asymptotes at all of the multiples of pi. Oops. It sort of repeats itself like that. So at x equals 0, that's one of our asymptotes. As we approach 0 from the right, cotangent goes to infinity. As we approach 0 from the left, cotangent goes to negative infinity. Then you multiply by 0, and then you say to yourself, okay, which one approaches 0 faster? Or does this function approach 0 faster than this function approaches infinity? If so, the limit will be 0. Does this function approach infinity faster than this function approaches 0? If so, the limit might be infinity. If they approach at approximately the same rate, then we might get a finite number that's non-zero here. But this case, sort of in the sort of battle between these two functions, like which one gets to its limiting value faster, quote unquote, this function sort of dominates. That x cubed gets to 0 faster than the cotangent gets to infinity in the vicinity of x equals 0. At least that's the idea. So if you have a 0 times infinity indeterminate form, so you've got a product and one of your factors approaches 0 and the other factor approaches infinity, if that is the case, then you want to rewrite that as a quotient somehow. Usually it involves taking the reciprocal of one of these and putting it in the denominator. So if I take the reciprocal of e to the negative 2x, I end up with an e to the 2x in the denominator. If I wanted to, I could have had an e to the negative 2x in the numerator and 1 divided by this function in the denominator. And then rather than having a 0 over or an infinity over infinity indeterminate form, we could have made it a 0 over 0 indeterminate form. The differentiation would have been more challenging though, so we wouldn't go in that direction. We'll go in this direction instead. Now, if you've got some trig functions that involve quotients of other trig functions, it's always good to rewrite those in terms of sine and cosine, and that will usually get rid of your product problem and turn it into a problem where you've got a quotient. And if this is an indeterminate form that's a quotient or a product, after you rewrite it as a quotient, you'll usually have infinity over infinity or 0 over 0, plus or minus infinity over infinity. Okay, so that's it for this video. Now in the next video, we're going to talk about these exponential type of indeterminate forms. There's a really cool one that gives us the natural base e. And then maybe in the fourth video, we will look at those differences, infinity minus infinity indeterminate forms. Say, is this one go to infinity faster? We get infinity. Is this one go to infinity faster? We get negative infinity. If they approach infinity at the same rate, you might get 7, or you might get 0, or you might get negative 12. Who knows? But we'll be able to handle that, and that'll be in the fourth video. So we've taken care of these two, and then this one, and then this will be for the next video.